Good evening. Today I will be presenting on the topic, the AI revolution towards the future of computer vision in agriculture, an engineer's perspective. First, we will start with a brief introduction, followed by a quick overview of the current trends and challenges. Finally, we will take a peek into the current research and future trends. Agriculture faces a number of challenges globally. There is this constant demand for agricultural commodities due to the rise in population, which has to increase by almost 70% than what is being produced now, to feed the 2 billion population rise in the year 2050 and around 1 billion already by the year 2030. Also, food waste is a known problem in different areas down the food chain, not only because of damage due to pests and household waste, but also because of not being able to harvest at the right time and not able to harvest all the produce due to labor shortage, letting the fruits and vegetables to just rot, surprisingly high of about 12%, summing up to roughly 1.5 billion tons of food. Speaking of labor shortage, which has been a common problem in agriculture for decades now, the younger generation are increasingly moving to urban areas, mostly for the lifestyle, and because they do not want to do physical labor in farms anymore. Finally, with all these happening, agriculture is the sector that is most susceptible to climate change and global warming due to its unpredictable weather and climate patterns. On the other hand, it is also the major source of greenhouse gas emissions that causes climate change in the first place, due to a variety of reasons, from soil management to food waste and management of livestock. These challenges demanded the shift from traditional farming to sustainable agriculture in an attempt to restore the resources that we have lost and to preserve the ecosystem for future generations. This shift already started in the 1980s, and it has been accelerating in the recent years due to technological advancements. The ultimate goal is to handle the challenges that we saw by using less resources and produce less emissions while still achieving high productivity and better quality. As we saw, the shift from traditional farming to sustainable agriculture already started in 1980s. In the early 1990s, people started using technology to achieve this, such as GPS to get precise location of crop yield or soil fertility, giving birth to precision agriculture. Only recently, around 2015, is when AI entered the field of agriculture, leading to the next agricultural revolution, Agriculture 4.0 as they call it. Thanks to the Internet for data and the GPU for compute, we would have noticed that AI technology has entered in every stage in the field of agriculture. But have we harnessed its full potential yet? The terms smart agriculture and precision farming have gained a lot of attention. So, where exactly are we right now in the midst of all these? At RoboVision, we aim to achieve EU's farm-to-fork policy by creating value with data over the complete food chain, starting from quality control of seeds to sort good quality seeds for sowing, picking and planting tulip bulbs based on size and orientation in 3D, harvesting tomatoes, weed detection and removal using drone and 5G technology, along with computer vision, to quality control of packaging the food and getting it to the retail market. This is how a typical AI pipeline looks like. Let's say we want to classify between weeds and crops in the field. We would first start with data capture on field to collect enough images of the crop and weed types to be detected and classified. When we have enough data, we will upload it to the RoboVision AI platform for the experts to label them. Once the data is accurately labeled, we use it to train a deep learning model. Finally, when we get a trained model with a high accuracy, we deploy it back on field to classify weeds and crops from the new incoming image samples. Also, worldwide, there are many AI-powered robots and technologies that have been coming up for autonomous harvesting, crop monitoring, livestock monitoring, weed removal, and many more. Although there are many AI-based applications used in agriculture, roughly 80% of the applications are still in research. And there are two major challenges along the way. AI, and in particular deep learning, thrives on data. Deep learning models can achieve really high accuracy without getting tired, provided we give them hundreds of thousands of labeled images or more to learn from. More the data, with all the real-time variations, such as weather, lighting, growth stages, different angles, and so on, better the results, depending on the size of the model. Data collection and labeling is a time-intensive and laborious task, and it has to be done for every use case from scratch, even within the agricultural domain, increasing the time and monetary cost. Most of the time, the collected data also lacks variation due to time and seasonal constraints. The next big challenge is the availability and usability of the technological resources, such as the high cost of the sensors. Also, AI algorithms depend a lot on the GPU compute, not only for training, but also for running inference on field and achieve the desired speed and accuracy. Given these challenges, let us see what the future holds. We know that 2D data has shown a lot of impressive results, and we know for a fact that DL has revolutionized a lot of computer vision tasks, surpassing human-level performance. Despite these results, 2D data misses a crucial information, that is, depth. With the recent advancements in 3D sensor technology at reasonable cost, like MS Connect and TOF cameras, has given us the opportunity to investigate deep learning architectures with 3D data more efficiently than ever before. For example, in livestock management, 3D deep learning has also proved to be more efficient than 2D deep learning techniques to capture anatomical landmark of cattle, segment cattle from shadows and dynamic backgrounds, and calculate their body condition score, BCS, and lameness detection score, which is helpful to detect healthy cattle from unhealthy ones. 3D deep learning has also shown promising results in plant phenotyping, where high precision is required for the robot to grab or cut. Although the GPU compute has evolved rapidly in the recent years, it still poses a significant challenge to process 3D data efficiently, memory and compute, forcing us to work with low-resolution 3D data, or to perform prediction in 2D, and then convert the 2D information to 3D in order to achieve results real-time. It is only in some more years to come that the GPU compute and perhaps the size of the model will further evolve to make this technology available to use in real time in a much more efficient way. So far, traditional AI models are usually trained on specific data set for a specific use case. The concept of these foundation models is to train the model on data with a diverse knowledge base, just like the base foundation of a building that supports the structure above it. Once this model is trained, this foundation model can be used as a base model that can be fine-tuned to various specific applications, instead of training a model from scratch for every new application. Everyone will be familiar with ChatGPT, the famous AI chatbot that took internet by storm, is also a language-based foundation model. This model was trained with 250 billion words to achieve such an impressive performance that it generates incredible human-like texts. This ChatGPT is a foundation model that can very well be personalized or fine-tuned with very little or no data for specific applications. For example, AgriOne and Norm are AI agriculture advisor applications being built on top of ChatGPT, fine-tuned to generate agriculture-centric texts to assist farmers on all queries about agronomy and farm management. The basic idea of foundation model is to have one model for several use cases. Like ChatGPT, Segment Anything model is a vision foundation model from Meta AI that was trained on 1 billion high-quality annotated images. But this model was also used to annotate 11 million images without any human intervention, and I think that is pretty impressive. This model was tested on poultry data to segment the cage-free hens from thermal images and achieved around 94% accuracy without any further training or fine-tuning. This shows how powerful a foundation model can be. It could indeed remove the dependency for any large labeled datasets to achieve a good level of accuracy. Although it was also tested to detect potato leaves and seemed to achieve an accuracy of only around 65%. This showed that there is still a huge gap to extend and generalize these for different use cases, even within the agricultural domain, especially when the inference space of training is limited. A foundation model that is trained specifically with agricultural data can be more powerful, making the agricultural sector less reliant on extensively labeled dataset. Multimodal foundation models are also becoming famous with GPT-4, where the input and output of the deep learning model is no longer of a single data type like text or images, but is capable of handling multiple data types such as text, video, images, and audio. For example, an agriculture-based multimodal foundation model can not only detect diseases in plants, but also interpret the type of disease, its causes and effect, and also steps on how to mitigate it, perhaps with audio and video assistance. With the wide range of variations and diversity in agriculture that also changes over time, it would indeed be challenging to collect data, including all the factors such as crop and weed types, in different growth stages, in different seasons, weather and lighting conditions, soil conditions, indoor and outdoor over a period of time. But it would be crucial to have a centralized data to develop a robust and efficient foundation model. It would indeed be a milestone in agriculture to have such a base model. We all are familiar with deepfake, in which AI tries to manipulate the facial expressions of a person in an image or video. It creates a fake data very similar to the real data, with some modifications that sometimes make it difficult even for us to differentiate between real and artificially generated data. This is done by using generative AI techniques. Same technology is used to create synthetic datasets to handle the data availability issue that I mentioned earlier. This image of the tomato plant here is artificially generated by generative AI technique. In the first glance, it looks very similar to a real tomato plant, isn't it? But when we zoom into the details, we notice that it misses to capture some important details such as the stalk of the tomatoes. That is crucial information that will be required by the harvesting robots. Hence, there are these special local attention-based generative models in research that focus on such issues. In future, as this technology matures, it can be very useful to address the data availability issue, especially when data capturing is hard or expensive, for example in different seasons, or when there are rare anomalies that have to be captured, without really having to wait for the data to be captured in real time. Augmented and virtual reality are budding technologies that have been a buzzword for decades now, but has been advancing more in the last 5 years. For example, in livestock management, there was a research to use AR technology to provide remote assistance through a video call to unskilled operators during on-farm activities like inspection of milk machines. Although it was easier for the operators to work hands-free based on the remote guidance with AR glasses, the scanning time and response time were quite high, making it challenging to use it real-time. For now, we can only imagine the potential of augmented reality when coupled with IoT, computer vision, and AI that can scan the environment, process the information on cloud, and overlay the insights from predictions on the phones or smart glasses in real time, giving us the ability to visualize information that we don't see with our naked eyes. They can also be coupled with GPS, in combination with other camera and EMU sensors, to get a higher location accuracy, as that is the ultimate goal of precision farming. On the other hand, virtual reality can create a whole new digitalized world, mimicking the on-farm activities that can be used to train people remotely and also to train farmers to use latest upcoming technologies. AI is already transforming agriculture, But augmented reality and indoor farming, along with AI, will be a breakthrough in altering the production and business models deeply in this sector. This combination can be a powerful tool that not only can provide assistance to farmers to achieve precision agriculture, but also motivates and enables beginner in farming like me to grow a small indoor farm for my household. I strongly believe that achieving sustainability isn't about few countries having the knowledge to be major producers and exporters for the rest of the world, but making every continent, every country, state, city, and perhaps every household self-sustainable, which can be possible with this kind of technology. We would have noticed that it is not just the AI algorithms that does everything. Therefore, true power lies in integrating with other technologies. Hence, there is a huge dependency not only on AI algorithms, but continuous research and development in other areas too. We humans always know how to work around. We know how to make something out of very little that we have got at hand. We are pretty good at that, and that's what has got us this far, even in evolution. We have already started to create applications with what we have got. It is indeed very clear that there is a lot more to come based on the researches that are going on. 50 years back, applying AI to real-time use case was science fiction. Now AI has revolutionized many sectors, most importantly computer vision, that is now playing an important role in revolutionizing agriculture. Hence, it is safe to conclude that the AI revolution in agriculture has just begun. It is happening as I speak, and the growth is certainly accelerating towards a better future. Thank you.